So today, as I noted, we're going to be going through further discussion of joining tables. We're going to see how aggregation is very important to consider during those tables, and naively joining tables, as we did last time, can cause challenges. Number two, we're going to be talking about a way in which we can turn data frames into data sets. I am going to introduce a kind of little helper function that will help us connect to Cassandra more easily. And finally, we'll also be introducing an additional helper function or two for dealing with Spark surveys, the Ethica surveys in Cassandra as accessed by Spark. Okay, so that's going to be much of today's lecture. In the process, I'm going to be pursuing this exercise that I asked you to pursue before. You folks should be able to see that here in just a second. Here we are. So I had asked you to pursue an exercise which had a kind of strange title. In fact, it has two strange titles. One, multi-level decision tree, and two, Spark joins has. And so I'm not quite sure what happened. Maybe too many late nights for me. So in this exercise, I asked you to perform some analysis using data from Ethica. And the exercise required you to link together GPS data with data from surveys. Okay? And then I asked you to use the analytics and the mechanisms within Zeppelin to visualize these things using pie charts and using, I had in mind sort of bar charts here in the form of these histograms, okay? So I'm going to go through my answers to that whilst talking about some sort of particular variants of them to sort of highlight certain things. So I'm going to go connect to Docker, to Zeppelin here. So here's Zeppelin, and I am going to go and rather than recreate it from scratch, I'm going to go and go to my pre-existing code for this, okay? The pre-existing code for this was a notebook that I created for this exercise and related things. And a keynote that happened when I created the notebook, I made sure at time of creation that Spark-Cassandra was the top interpreter. So by default, that is the interpreter whose the default interpreter, the interpreter that we're going to use for these notes if there's no annotation. Okay. The second thing that I did here was to import the connector. This is the Spark Cassandra connector, and in importing it, I am moreover starting up the Spark shell. So the first time I do that, it takes a bit of extra time, okay? Now, I further am going to introduce a little helper function here, which will make it easier to connect to Ethica databases, okay? And specifically, there's a set of actions that are very common with Ethica databases. They include, number one, loading the database in from Cassandra with some standard structured information. Number two, adding time-slotted data, sort of classifying it into a set of time slots, and finally, caching the results. So what I'm going to do is to put those into place. And this time slot thing, which is the next one, should really be above it so that this is available. So there's a time slot from timestamp UDF. And basically what's going on is here, it's dividing up things into 10-minute. This function says, given a timestamp, it'll classify in what 10-minute time slot it's located. 10 minutes, this guy here. We saw that last time. Remember that? So that's a UDF. It takes a function which operates on values, namely timestamps, and turns each value into a time slot number, to instead being a function that operates on whole columns. And by virtue of that, we can apply that UDF to the record time column and create a new column called time slot here. Now, truth is, there was a race condition. I actually couldn't finish this quite on time because I wanted a more general version of this where the time field is not hard-coded as record time, but instead is just that by default. This is the Scala syntax for it. It is this parameter where this is the default value if you don't specify it. But I actually wanted to get a column with arbitrary names that the user could specify time field. And I just didn't have time to sort of go put in the requisite syntax for that. So I didn't have to do this $, whatever. This $, with the quoted thing, that's used to denote a column with in the current data frame or data set. But it doesn't, as I recall, you can't do $, the name of a variable. Instead, you have to get the column in a different way. And I need to do that there. We may come back to that. Okay, so then using this mechanism, I didn't execute it. Here, let me define this. There we go. Using that mechanism, I then loaded in this GPS table, okay? And in a manner of speaking. In fact, what happened is that I didn't load it. I lazily queued up the plan to load it, right? And we did, however, in so-called loading it, learn what its schema is. The schema is as follows here, okay? So we have user ID, we have device ID, we have things like latitude and longitude, and importantly, we have accuracy for the sake of the exercises. Okay. More than that, because we read it by calling this function we created, it's actually inserted a time slot here. And the time slot is a long value, which indicates that the absolute value is not that important, but what it indicates is the 10-minute time slot, an ID for the 10-minute time slot, right? Now, we could, with this data frame, as with others, ask information about what operations are performed for it. And here, it's actually telling us sort of how it's deriving that data set, et cetera. Okay. And there's some caching involved in this data set, and there's some reading from a Cassandra source. Okay, that was just for our interest. We may use a similar thing later, later in the session to track things. So here we go. Having done that, I'm filtering the data set to user 231 to get the user-specific data set. And actually, I don't need this anymore. In fact, this thing, I kind of was frobbing this because I already have a time slot. So I don't even need to do that because I created that extra thing in that function. I'll just do df time slotted GPS equals this guy. Okay, so here we go. We have a time slotted version of the GPS there, okay? And if we were to look at this again, one of the things we would find if we did this to debug string, this tells us the lineage of what's going on here. So if we were to go do that, what we would see now is we have a okay. That's interesting. Would have oh, of course. What didn't I do? Why is this just like that? I didn't do it for the new the results here. I just did it for the original thing. That hasn't changed. What's changed? What's where we'll see the real big differences is here. Okay. I would have expected to see the results of filtering it. Okay, I'd have to come back to that to see why. In any case, what I'm going to do here is check how many records, and this gets into my next point about the importance of aggregation. This is something we did not do last time when we talked about joins at a naive level, but it's very important to do. And you should realize if you don't do it, it may be done for you sometimes, okay? So here, I'm going to check essentially how many of the GPS records are at different time slots, okay? So if we consider a given time slot, how many GPS records are there at that time slot? If there's just one per time slot, then there's no need to aggregate if we were to join sort of a group by time slot. On the other hand, if there's many, then there may be many discrete readings for a given time slot for a given user. And that could pose challenges because we need to be able to join it up uniquely with a survey. We don't want the survey to have a single survey to have 10 different mappings to different GPS locations, depending on the vagaries of whether if 10 particular GPS readings were made during that time slot. We'd like it to have one best guess reading, okay? So if we do this, here we're grouping by time slot. It's already specific to a user here. It's already specific to this user ID 231. If we group by time slot and we count the number of records in each of those time slots, what we'll find is that a given 10-minute time slot can have a lot of readings. Some can have few. This one has one, this one has two. Probably the phone carrier or tablet carrier was inside at that time in a big building. Perhaps the very building in which we now sit. Okay. In other times, the sky was wide open, as it often is in Saskatchewan, and you know, he had 108 readings. Okay, so in short, we have to be careful here because each time slot has not just a single reading. Consider when we're joining it, but many readings. And as I say, when we join that together with the survey, when we sort of label the survey by where it occurred, we really don't want to have 10 different labelings or 108 different labelings of this survey that happen to fall in its same time slot. We instead want to label it with one consensus estimate. So the next set of actions are going to relate to that. And I'm going to rearrange this a bit visually just so that you could see it more easily, because I did this on a monitor that's bigger. It's not as big as the Wadarian monitor, but it's a decent sized monitor at home. Okay, so what I'm going to do is the following. This is going to walk us through a few things. First of all, I'm going to narrow down what I'm dealing with. I actually am going to jettison some of this stuff up here that we don't need. For example, I'm not going to keep any longer the provider, which is a string, okay? For the analyses I'm going to be conducting below, I'm not really particular about the provider, nor am I particular about the satellite time, okay? And device ID, I'm also going to jettison it. All I need to know is that it's the user I don't need to know if was it his tablet or his phone or what have you. So in short, I'm narrowing it down to these fields. I am then going to group by the time slot, okay? By grouping by, what this is referring to is I want to combine together the values for a given time slot, so a given 10-minute interval in this case. Now, when I do that, when I say, hey, all 108 of these GPS measurements taken during time slot 2489328, these guys here, if I were to take all those, I'm going to turn them into one consensus estimate. And how am I going to do this? Well, in a simple way. I'm going to take the average of their accuracy, of their latitude, their longitude, and their speed. Okay? Now, it may be obvious now why, for example, I got rid of provider, which is a string, because then I'd have to deal with the fact that, if during those 108, there were sometimes it was getting it from Wi-Fi and sometimes from the satellite and so on. How am I going to turn those into a consensus string? Well, maybe I would have appended them, but I didn't want to get into that. It's not really germane to our analysis. So I'm going to combine them. I realized this wasn't something I talked about last time, but in pursuing the exercise, I realized it was something I have to talk about. Hence, I don't expect anyone here to have done that. If someone did, my hat is off to you. My bike helmet too. Okay. So here we go. Now, DF time slotted narrow. Let's go check what's going on here. To Java RDD, to debug string here. So now we've got a lot of things going on, and there's added work associated with sort of the aggregation here with these various steps of its operation. This you'll notice that this is being projected down. This projection relates to, as I recall it, taking all these broader set of strings and indeed just projecting them into a smaller set, this set of 6 here, okay? And then there's this averaging that's occurring over all of them. But the point is, it hasn't all been done yet, okay? Okay, so so that's good. Let's take a look at just what comes out of this, right? What comes out of it, just to give us a bit of concretes here. Now work is actually going to be done more heavily, and this is what we're getting out. So these numbers, latitude and longitude, accuracy and speed, these are resulting from aggregating many particular measurements by averaging them, okay? And the labels like speed came from this label, not from this original label. We're aggregating it. We could have called it average speed or whatever, but we still have it for the particular user slot and time slot over which we grouped it. Okay? Okay. So we have to deal with that. Now, let's go read in the survey responses here. There we go. So here are the survey responses. We can print the schema for this, and we'll find, well, the other one was a bit textured. This one is yet more so. We have this map, you may remember, for responses from integers to strings. We have the time slot, which has been added. We have the survey and sub-survey, etc. So I added this response category. I don't think this actually has to be here, but I'll execute it. And then I wanted to get the survey responses specifically for the user. This says sampling survey, that actually just should say user specific. Also, here I am, oh, this is not needed anymore even, since it's done above. I mean, it's fine. It won't hurt, but that should be okay. So I'll re-execute that. Boom. So in other words, I didn't have to add the column for time slot because now it's done as part of this load right here. Okay. Okay. Continuing on down. I then thought to do something very similar to what I did above, where I showed how many records were there from each time slot. Remember this? I grouped by the time slot and I counted up the number that fell in that time slot. I did the same thing for this out of curiosity. And what I found is that for this user, most of the surveys, well, what is this telling you? What are all those ones tell you? What is this telling you? For each time slot, what? Yeah, the user was answering at most one survey here for each time slot, right? Well, for most. But then there's an occasional two, where the user answered two surveys quickly in short succession within a 10-minute slot, okay? So what I decided to do based on that is, look, this is all leading up to this join, which is here, right? And for the join, I really wanted to make sure that we were dealing with, for a given time slot, not multiple values, but in fact, one consensus value, an aggregated value estimate of location. Because otherwise, maybe for a given time slot, we have one survey, but 10 different GPS readings. And what would happen then normally with our join? What would we get out? What would we get out of our join then? What would we get out? We get 10 different joined together of them. We'd have one, a record for the same survey responses for all the different GPS locations in which were recorded in that time slot. I didn't want that. I just wanted one. Now, if there's 2 surveys in a given time slot, or 5, where I filled it out, I don't have a problem with each of them. By the way, I'm running this. I don't have a problem with each of them being reported for that time. It's not like I want to take all surveys from that time slot and combine them. After all, this user might have answered different surveys, survey of type A, survey of type B, survey of type C. We can't realistically, nor do we want to just mush them all into one survey response just because they happen to be in the same 10-minute time slot. Okay, so what I did here is I joined together this, and I'm going to say cache. That means, hey, try to keep it in memory if possible here, okay? It's important to keep in memory. I'm going to use it a lot. And then what I did is I created a thing called Survey GPS. This is actually a table that I can access from Cassandra SQL, okay? Now, all this was preparatory, and I'm now going to show how I did that, how the sort of final steps I used to deliver this, okay? So what I've got in place is my GPS data. I've got in place my survey data. I've got in place my join of them, not with, imagine if there were 5 surveys, 10 GPS readings previously. If I hadn't dealt with that aggregation, I would have gotten 50 different combinations, which wouldn't have been conducive to real insight. So here I've joined them together more properly by aggregating the GPS. And that puts me in an excellent position, a position of strength to visualize the count of surveys that fell into different categories. Now, to do this, I want to highlight something. It wasn't obvious that I did it. But I had this response category thing I defined earlier, response category UDF. That was something that basically classified a given survey based on the reported duration it classified that survey into three possibilities. It was answered, it was canceled, or it was expired. Okay, you know, I could probably improve that function a bit, but the basic deal is that this function this UDF takes a function which operates on a given duration, like -2 or 5, and it turns it into a string, right? Turns it into a string like this. And by taking a UDF of it, now it's lifted to the domain of columns, data frame columns. So I can apply it to duration column and get back a column, which I called response category. So having done that, now I have a response category in this join survey GPS. Let's go look at what that join survey GPS is. Here we go. Print schema. Here we go. There we go. Here it is. What's there? Okay. Well, there's some of these things. Whence did these come? GPS. And then there's some of these guys. Whence did these come? Survey. What are these two guys? They were the keys. They were the keys that were matched up to allow the join to take place, right? It is, you could see they were matched up here, okay? So this has got what we've got. You'll notice that if I were to look at the count here, if I were more artful, I'd have started this a while ago, because this is where things get more, can get a little bit slower. 2891, 2,891, right? If we just looked at DF GPS, DF survey, I don't know, is that what it was called? DF survey responses.count. This is something we defined above. 6,946. Why the discrepancy? This is something we should be aware of. Why are there so many more survey responses here than joined ones? It's an inner join. And what does that mean? Yeah. Yeah, well, okay. So yeah, if there's no matching time slot in the GPS data, it's going to be omitted. Why would there be a missing time slot in the GPS data? Because no GPS was picked up during that time slot. Could that happen? Yes, it could happen. Why would it happen? Could you give me? You're inside a big building. A big building. That's right. You're in an inner office in a big building. So that's one reason. One time we wanted to test this. So I, together with a set of students, I think William was with me, I remember that clearly. We went down into the basement of Thorvaldsen. Thorvaldsen has not just one basement, but two basements. I think we tried to go to the bottom basement. We could only go to the upper basement, I think. But anyway, we wander way into a machine room, and there are all these fans going and stuff like that. And we stood there for more than 10 minutes to guarantee that we had, a time without GPS. And indeed, there's no GPS. So that's one reason. Why else might it be missing GPS? Turned off. Yeah. The user turns it off, turns off location-based services, right? So it can happen. And in other cases, with Ethica, a user might pause with snooze. They might say, snooze my data collection. So just be aware that you can't always assume that if you're going to do a join, that all the data from both tables are going to align perfectly. And we'd probably be interested in take a look, which are the surveys without corresponding GPS information? You know, are there something unusual about them? Maybe there is. I'm not going into that here, but just be aware that when you're doing a join, by default, it's an inner join. You can perform other types of joins within Spark. Okay, so we went and we created this table, which allows us to use Spark SQL. Now I'd like to address the sort of final rounding thing. So I said, create 2 pie charts. How often user answers surveys under different contexts. So each of the pie charts is going to visualize the count of survey response categories, each of these categories, for 2 cases. One where it's below GPS accuracy below 30 meters, and the other where it's above 30 meters. So here's where it's less than. So I say the accuracy is less than 30 meters. I actually stand to be criticized for that. Why is it a little bit misleading to say accuracy is less than 30 meters? Okay, first of all, it's average. Very good point. It's average accuracy. The second thing is that if I say accuracy is less than 30 meters, someone could naively think I mean, oh, we have poor accuracy, low accuracy. In fact, this is when accuracy is the highest. This 30 meters is actually the standard error, as I understand it, associated with the estimated, it's the estimated error associated with the GPS signal. So if you're looking for less than 30 meters, you're talking about a situation where your location is being estimated with confidence within a less than 30 meter sort of radius, okay? Let's suppose we're 10. That would mean the satellite or Wi-Fi systems are allowing my location be determined within about 10 meters of here. That's pretty accurate. That's actually gaining accuracy. But unfortunately, the way it's encoded, we have to say accuracy, you know, accu less than this. So this is actually more accurate cases. And what we could see here is that most are expiring and a minority are being answered. Just a few are canceled. After all, canceling takes active work. Like I have to say cancel. Okay, how about when there's poorer accuracy? There's accuracy that's more poor. Okay, here, okay, that's an interesting thing. It just updated significantly. So here I have even more of an imbalance. So the answered ones are 15%, and the expired is 82%. Okay, so here I have poor accuracy. Presumably, I'm in a large building, or some other context that's blocking GPS, and I'm having an even smaller fraction answer. Okay. Okay. So that was number 1 here. 2 pie charts. How did I create those pie charts? I used this SQL. I drew data from survey GPS table, which we have created here. I grouped it by response category, and for each response category, remember this is a string, like answered, canceled, expired. For each, I counted the number of cases for that. If you looked at this as a table, this is what you would see, but we chose to look at it as a pie chart. Okay, here we go. Okay. Now, for the next 2 things, we needed to classify things into histograms. We were creating histograms of surveys which had a certain level of accuracy, where accu fell into certain bins, okay? And I should have made that a little bit clearer in my description. So in order to do this, we need to make use of some math functions. Below here, I make use of two. I make use of a function floor, which takes a double value and maps it to a double, which eliminates the fractional part. So if it turns into the nearest integer less than the actual value. So if it's 67.2, it turns into 67. If it's 67.9, it turns it into 67. So I use floor, and I'm also going to use round, which turns a double into a long. Okay. So here I'm going to import Scala Math, and that is going to give me these things, so I don't have to use it explicitly. So I'm going to declare this accuracy bin for 5-meter bins. So what I'm going to basically do is I'm going to take the accuracy. Let's suppose the accuracy is 16 meters. So it's 16. I'll go through this little deal here where I'll divide 16 by 5, getting 3.x. I'll take the floor of it, getting 3. That's the next lowest number of times that, or the next lowest integer would be 3. Here would be 3.0. In terms of the number of times 5 goes into 16. And then I'm going to multiply that times 5 to get 15. Okay, so in other words, I have 16, divide this by 5, I get 3.x, take the floor, you get 3, multiply it by 5, you get 15. There I go, right? Yeah, okay, this is the number of times that 5 goes completely into accuracy, right? It goes 3 complete times, yeah. Okay, so let's run it. There we are. Great. So that's our UDF. Again, this is a function that applies to values associated with accuracy. And by UDFing it, we have something that can be applied to columns. And we add a column called AccuBin accordingly. Boom. There we go. Okay, and now we create a little table. Okay, having done that, I stand in a good position to deliver on number 2. So what do I have to do? Well, I want to, for each AccuBin, I want a histogram involves having a set of bins, and for each bin, you do what? Count the number of cases that fall within that bin. So for each of these accuracy bins, I'll count the number of surveys whose level of accuracy fell within that bin. Okay, now, when I first did this, late last night, when you were all in bed, perhaps, I was doing this, and mumble. Okay, sorry. Group by. What I meant to do is this. Sorry. This is what I did initially, and I got something most unpleasant. What's going on here? It's not ordered. It's not ordered. There's not particular rhyme or reason for it. It seems, I have accuracy bin 0, and then 75, and then 35, and 25, and 50. Beats me as to why it's in that order, but no worries. I just put in an order by in the SQL, and here we get them nicely ordered with each accuracy bin successfully rising, and I can turn it into a nice chart. Okay, here we go. Okay, So that's for the answered case. The other cases can be graphed similarly. And it's worth looking at them. What is this? What is this saying? So answered ones, well, it's almost like an exponential distribution. Not kind of like a shifted exponential. So it's interesting. It seems that fewer of them are answered within the first couple minutes, the first 5 minutes. There's only a small number of 14. Of those that are answered, it seems that most are answered in the first 5 to 10 minutes.
15 minutes.
Well, oh, this is accuracy. I'm sorry. Sorry, I had a similar one with duration. Sorry, I'm out to lunch. I showed that to you before. That was a previous lecture, not this one. Yeah, no, this is accuracy. Okay, so very few have accuracy that's very precise. There's a preponderance. The single most common one is 5 to 10, right? 5 to 10 meters, which is highly accurate, actually. Probably caused by, what do you think? Wi-Fi location, turns out. Normally, I don't think I'd get that. Well, we could check how many of those come about with GPS alone. That'd be an easy thing to check. We'll probably do that in a minute. And then successively, it's smaller and smaller. Interestingly, looking kind of exponential. Here we have for expired. You notice expired is a little bit different in its characteristics. Not only are the counts somewhat bigger, but it's also tends to be a little bit to the right of that one. We tend to have more long tails and sort of this sort of second peak here. Okay, and then here's canceled, and that's very small counts, and it's got some higher accuracies. Okay, I mean higher, poorer accuracies, larger uncertainties associated with it. Okay, suppose we wanted to find out which are these ones that have highly accurate values there. How do we do that? Like, are they from a network provider, through Wi-Fi, or are they from instead a GPS satellite? How do we do that? Well, I'll just mention that, I'll just remind you that we discarded provider information here. So we actually got rid of this here, but that's okay, because to answer this question of which ones are those, we actually, to answer it in general, putting aside the issue of whether they were answered or not, we could actually just use DFGPS, okay, which is this data set we started with. And this one, in fact, has the provider, okay? So how would I answer that? Suppose I wanted, with DFGPS, by the way, I'll provide you an updated version of this after we're done. If I wanted to go look at, I want to check DFGPS. I want to create a chart to look at who are the different providers based on different levels of accuracy. What would I do? What could I do here? Well, one thing I could do immediately, do I have to do much processing? Oh, I could go more or less immediately into SQL, right? Here we are. So I will do df GPS, put it right into GPS table. How's that? Okay. Okay, now I'm going to put in a Cassandra SQL thing. Okay, and what could I do? You can tell me. Suppose I wanted to look at what are the different providers overall. Let's do it regardless of accuracy. What's the breakdown by provider? How would I do that? Yeah, good. So tell me what to type. Yeah. Good. Counter provider from GPS group by good provider, right? Okay, here we go. Okay. A lot of values. Right. So I believe, and we'd have to look into this, but I believe the GPS and GPS. Okay, I'd have to be careful about what the passive means, but this is the overall characteristics. So I think GPS is actually satellite. I think maybe this is a combination. Maybe someone could look this up. What's that? Oh, some other application requested and received it from GPS satellite. So GPS passive and GPS are both via satellite. A network passive and network are both with the Wi-Fi network. Cell tower and Wi-Fi, and then fused and fused passive combined the two, I guess, probably, but it's a little bit moot because they're very few. Okay, so now how do we do this if we want to look very specifically at those who are low accuracy? Or those whose ACU value is small. In other words, there's low uncertainty. How do we do it? Yeah. Sorry. Actually, we need to put it in here, right? Or ACU is less than. Let's say because we were talking about this. Let's say less than 20, because we were talking about sort of this peak here between 10 and 15 that was predominant. So let's say less than 15. Okay, group provider. Yeah, there we go. Okay, and then let's. Okay, the GPS is still. Oh my gosh. Okay, so my theory was off. It was a beautiful theory ruined by an ugly fact. And then let's do this for greater than 15. Let's try it for well, sure. Let's try this. Okay, and now network starts to be more dominant. Okay, so I was thinking incorrectly that Wi-Fi network was the source of more precise measurements, but in fact it would appear quite the opposite, right? It appears that Wi-Fi is a source of less accurate measurements, and it furthers the point that inside my location tends not to be that well measured. Okay. Anyway, okay, so we're moving on to the final challenge. Okay, the final challenge here. So the final challenge took this one, which we just addressed, but it asked you to pursue it in a way that was a little bit trickier. And there's two components that made it tricky. And realistically, I probably should have split it into two subproblems. Number one, I asked you, instead of using uniform bins of width 5, for example, such as it was implemented by this guy. Here we just had bins of 5. No matter how big it was bins of 5. Here, we want to have different bins. So if we're dealing with accuracies that are in the small range, like less than 30, we want bins of width 1. Otherwise, we want bins of width 10. Okay? So that was one challenge that made it tricky. But then I added an extra layer on there. I added an extra layer of asking you to look at density. And you may have wondered, why did I do that? It may have seemed adding insult to injury, so to speak. Maybe none of you vocalized it in quite that way, but I could understand if it made you feel that way. So, ladies and gentlemen, let's go see why I did that. Why did I go look at density? Let's do it without density, shall we not? Shall. Okay, here we go. Here's accuracy quantum, okay? I'm going to define, this is a function here, and I defined a UDF based on this, okay? This is basically UDF, which can apply this to columns, okay? Now, suppose that I were to take these guys here. I'm just going up to copy a bit of code. Suppose I were to take that. I have this accuracy quantum. It's basically a more refined accuracy bin is the idea. And I am going to say, we're going to create a DF, it's a data frame, okay? And it's going to be DF survey GPS extended. Here we go. Hey, get over there. Okay. Naive bins. And basically what we're going to do is we're going to add in to this with column. We're going to add a column called naive bin. What do you think? And it'll be the result of applying accuracy quantum UDF. The UDF for it, right? Autocomplete is a little bit flaky, and that's, sorry, accuracy quantum. Accuracy quantum UDF, this guy. We're going to apply it to which? Well, we're going to apply it to what? Accu. There we are. And then I am going to insert that. Hey, get me back. Okay. Then I'm going to create from that. So here we are. Boom. Hey. Okay. DF join. Oh, what am I missing? Val, indeed. Okay. And I'm going to do this, and I'm going to call it survey GPS wait a minute. Do I really want to do this? Sorry, folks. I'm doing it to. I don't need to do it to the join stuff. That will actually take longer potentially. So time is short. So I'm going to actually do it. We're just going to, since we're just working with GPS data right now, I'm just going to do it with. Oh, sorry. No. This is. We want it for both. Okay. So here we go. Yeah, that's correct. Yeah, we're doing it. Okay. There we are. And here we go. We're going to do survey GPS extended, and we will call it naive. Okay, ready? Okay, great. Now we think we're cooking with gas. Okay, so let's go graph this out. Here we go. Okay, and now I'm going to use a similar mechanism to what we did above, right? This guy here. And we're going to do it here, all right? There we are. Okay, and we'll do it for answered. But instead of dragging it from this, we'll do it from this, right? Okay. Okay, and let's try this. Doing the computations, it has different, what do I want instead of this? I need naive bin. Well, it sounds good, but it sounds naive. Okay, here we go. Okay, here's our naive bins. We ordered by. Let's check this out. Okay. Now this naive bin, it did this for range less than 30 and above 30. Okay. Now 30 here was at this breakpoint. Do you see something a little bit artifactual above it?
Seems like we have more at 30 and then another 50. So
yeah.
The bins are wider, so there's more.
The bins are wider, so it's natural that more things fall within these. So I'm not really comparing apples with apples here. If I'm using these naive bins, these ones here are bigger than these ones, largely because they're wider. They're collecting more things. So of course there's going to be more things in them than their nearest neighbors over. But really what I'm interested in is kind of the density. It's sort of per sort of extra bin width, how many fall in there, okay? And so this has introduced this artifact, and it would have been more pronounced. I mean, watch this. I'm going to make it at 10. I'm going to make it at 10, okay? Or make it at 15. It's gonna be much more obvious yet. If I did that at the naive, here we are. If I did this at naively at 15, here we go. And we were to do that, I'll just show you how clear it is and how much it makes a difference. So this is this accuracy quantum. Here we go. And I'm implying it. And here we are. We're going to replace the table. And here we are. We're going to be applying it here. Boom. Okay. So now I did it at 15. And okay, now that's, yes. And so now you have to jump up once again here. Okay. So so in short, it leads to these artifacts. So what do we do instead? Okay, so the process here is is a little bit straightforward. First of all, I'm going to change that back to 30 so we could see that. I'm sorry, I forgot it was used below. There we go. And I am going to redo that. And for good measure, I'll do that. Okay. And now below, I define a second thing called accuracy quantum width. Okay. This is going to specify the width of the uncertainty at different points. Depending on where we are, what's the width of the bin that we're in? In certain ranges, it's going to be 1. In other ranges, it's going to be 10. We're going to be able to take advantage of that. Okay, now, what I'm doing further is I am going to take, I defined a function whose job in life is to determine the density. How does it determine density? Well, it determines it as follows. It's given the accuracy quantum, and it's given a count for that quantum. Yes, the accuracy quantum, and it's given a count for that quantum, and it takes the count and divides it by the width that applies. Okay, and that width is going to allow us to sort of normalize for the width of the bin. Okay, so we're going to get back a density, a sort of a count per unit of sort of accuracy measurement, accuracy width. Okay. Okay, so mumble. So what just happened here? I just rearranged this. Class IW needs to be abstract. Okay. This is interesting. Did I omit? Do you get the same error? Okay, did I cause a problem by deleting something here? Okay, let me forgive me while I debug this. Well, okay, maybe in the interest of time, I'll just leave that for a moment. I'll come back and debug it later. So what I did then to sort of finish the narrative arc here, I took this extended GPS. I added in a column called accuracy column, and accuracy quantum rather, and that just had the bin, the non-naive bin, and then I got the count for each response category that fell within that quantum, okay, because I knew I wanted to break it down by category. And then I created a column for the density, which was based on the count and the accuracy quantum, using this UDF that I just defined up here, okay? That allowed me to then arrive at a data set which contained a density as well as the other components. And I then went down and, okay, I sort of frogged around for a while. And then I went and I graphed this out. So I graphed out accuracy density for each accuracy quantum, and got something that looked like this, which was a density histogram for the case of answered. I got a one for the case of expired, and we've got one for the case of canceled. Okay, and you'll recall that the cut point 30 is here, and you can see that it doesn't have any sort of obvious artifacts associated with it like before. There's some fluctuations, but it seems to basically be correct in its density estimates. Okay, so that's how I did that, and that completed this third component here. I am now just going to debug this guy because I'm intrigued as to what happened here. I'm just going to say this. Let's say 1.0. There we go. Let's just go see if the same error comes up. Fascinating. Oh, I bet I know what it is. What's this? Oh man. There we are. Okay. Now we're happy. The parser sometimes is not that great. As you can see, I think what I did is I divided that, and now I guess it's trying. I don't understand why it thinks this is done, because there's still an unclosed parenthesis, so I wouldn't think it would think that's a line by itself, but I beats me. That's weird that it has that sensitivity. Anyway, now it works fine. Okay, so that was that component. Next time, we're going to go on to just make 1 or 2 points about this, but then we're going to be introducing Spark streaming. Now, one thing that I did here was I'll highlight to you next time is the possibility of operating on these data frames as fully typed data sets. And the key thing we're going to have to do is define a case class, which is going to define statically the structure, the types associated with the data frame. And having done that, we can then, if we're dealing only with these fields here, we can actually just declare it as a data set whose rows are members of this class. Okay, and having done that, we can then operate on it in a type-safe way by doing things like this. Okay, we don't have to do, for example, filter by duration, something like that, referring to this. Instead, we can just operate on sort of familiar operations. Okay, so I'll show you a little bit of that next time. There's a slight wrinkle in that it's finicky, and there are certain complex structures like this map of responses where it can be a bit truculent, converting it into a fully typed, strongly typed form. Okay, that's all for today. Thank you very much for your patience going through that. I hope the VPN comments will be of help. I'm glad we were able to go through the exercise more carefully. Thanks very much. Yes.
In the next lecture, are we going to cover some?
Yes. Yes. Yeah. We're going